Modern enterprise supply chains possess nearly infinite data visibility, yet they are paralyzed by extreme decision latency. You can track every container, but if determining how to route them takes 5 days of cross-departmental alignment, the operation remains effectively frozen. This diagram illustrates the traditional linear system of record. Data from isolated ERPs is exported into spreadsheets and static dashboards. The flow stops at a human bottleneck, pushing the decision cycle into days or weeks. Now look at the right side, the system of action. Data feeds into a central core, instantly delegating tasks to autonomous nodes, verifying a corrective action in under 60 seconds. This structural shift represents agentic commerce. It bridges the gap between planning and operations by giving software the capacity to execute multivariable decisions autonomously, rather than just reporting on them. Achieving supply chain resilience requires recognizing that you do not have a visibility problem, you have an orchestration problem. The solution is moving from a posture of static observation to a continuous system of action. Transitioning to agentic commerce requires engineering a highly specific structural stack. It cannot be achieved by purchasing another standalone dashboard, nor does it require ripping out your existing infrastructure. This is the exact problem Pluto7's planning-in-a-box framework solves. Built natively on Google Cloud architecture, it sits directly on top of your existing systems of record. The engineering challenge is strict. Ingest fragmented enterprise data, safely weigh conflicting operational priorities, and autonomously execute a verified response in under 1 minute. To prove how a 60-second autonomous supply chain decision is technically achieved, we will deconstruct this agentic enterprise architecture layer by layer. Autonomous AI cannot function on fragmented silos. These heavy, isolated blocks represent standard enterprise architecture: SAP, Oracle, Salesforce, and IoT. They don't communicate natively. To establish a single source of truth, we implement Pi. Unify the disconnected nodes, dissolve into a real-time data foundation. This layer seamlessly ingests both structured database tables and unstructured document files. It standardizes the inputs without requiring the business to replace its core systems. The system also actively pulls in external environmental signals. Weather patterns, Google Ads performance, and global market indices drop directly into the foundation, providing immediate real-world context to internal metrics. For a modern supply chain, scheduled batch uploads are obsolete. Operating a responsive network requires real-time, event-based data feeds to capture constraints the second they materialize. By organizing chaotic, disjointed enterprise logs into a reliable agentic data cloud, Pi Unify establishes the strict factual baseline required for machine reasoning. Unified raw data is structurally sound, but it lacks business context. Without relational mapping, an AI cannot determine how a delayed shipment affects a specific retail promotion. This brings us to the second layer, Pi Semantic. Built directly above the data foundation, this is the intelligence layer. What you are seeing is a semantic knowledge graph. It functions as a literal digital twin of the physical supply chain. Notice how the central customer node connects directly to inventory, logistics, and weather constraints. Because of these explicit links, if the system detects extreme weather, it instantly calculates the cascading impact across the network, accurately mapping the exact mathematical risk to a specific customer segment. This is not a traditional relational database querying static tables. It is a dynamic, real-time math of operational reality. By defining these complex relationships, the Pi semantic layer gives the system the spatial and business awareness required to navigate difficult trade-offs, like balancing carrying costs against required service levels. At this point, the primary objection from any enterprise architect is risk. Granting autonomous execution capabilities to an AI system is a severe liability if there are no ironclad guardrails in place. To mitigate this, we deploy the third layer, Pi Shield. This is the governance and security layer that encloses the entire intelligence stack. Automated data quality frameworks act as a physical barrier. Corrupted or hallucinated data is blocked from entering the central ledger, while identity access, row-level security, and data lineage protocols run continuously in the background. Pi Shield guarantees that every automated decision is policy-compliant, entirely traceable, and strictly audited. Enterprise-grade security is not a bottleneck here. It provides the mandatory verification required for machine speed execution. Monolithic algorithms routinely fail in supply chain planning because they cannot simultaneously balance competing global KPIs. Finding the cheapest freight often contradicts the needs of the fastest delivery. The solution is the final architectural layer, Pi decision. Here, the central orchestrator, the Pi agent, takes command. Instead of processing tasks linearly, the Pi agent delegates complex, multivariable problems to an autonomous council composed of over 100 highly specialized microagents. Each agent has a specific mandate. Take Ron, the demand sensing agent. He adjusts forecasts using market signals. Cassie handles global inventory positioning. Sam calculates critical supplier risk, and Larry optimizes logistics routing. This enables parallel solving. These agents negotiate risk, cost, and time parameters concurrently, communicating through agent-to-agent protocols. They utilize the semantic knowledge graph we built earlier to rapidly iterate through conflicting operational priorities, testing thousands of variables against each other. By fragmenting massive supply chain problems across specialized microagents, Pi Decision collapses what used to take days of cross-departmental alignment into a 60-second execution window. To see this architecture applied, look at this map. It's late November, and a sudden, unexpected demand spike for a specific SKU triggers a red anomaly over Atlanta. The agent instantly detects the anomaly, delegating parameters to demand, inventory, and logistics agents. As these overlapping lines show, they run 10,000 digital twin simulations in the background, calculating exact trade-offs between transportation costs and lead times. The agents filter these simulations to identify the optimal path, maximizing profitability and network resilience. The output is precise. The system isolates a surplus in warehouse A, generating a verified recommendation: move 9,800 SKUs to cover the Atlanta shortage. Upon human approval, or autonomous threshold clearance, this strategy is written directly back into your ERP, TMS, and CRM systems instantly. A problem that traditionally required emergency meetings, manual spreadsheet analysis, and days of operational latency was just sensed, solved, and executed in under 1 minute. This system uses a glass box methodology for practical autonomy. Agents execute routine operations autonomously, but high-impact decisions trigger exception-based workflows, ensuring humans retain final oversight. Because the reasoning is transparent, human planners can query the agents directly using natural language to trace the exact logic behind any decision. In this model, the supply chain planner's role evolves. No longer manual data aggregators, they become AI conductors, orchestrating a self-healing network. Removing latency directly lowers operational costs and shifts the supply chain from a reactive posture to a proactive growth engine. In the era of agentic commerce, true competitive advantage belongs to the enterprise that orchestrates actions in seconds, not the one that plans in months.